Hi, welcome to Minja's YouTube. I am Minjae Kwon, mechanical engineering student at NI University, and I'm going to introduce numerical model of the new aluminum reduction cell. Aluminum reduction cell focuses on better yield for pure aluminum, which is illustrated in this figure as metal pad. Aluminum ions are reduced near cathode where sufficient electrons are present, whereas oxygen ions are oxidized by emitting the carbon anode into carbon dioxide. As you can see here, interface chemical reactions from liquid to gas takes place in the cell, and therefore, aluminum reduction process represents a multi-phase flow, including multi-phase mass transfer and electrochemical reactions. Moreover, since complex chemical reaction steps are coupled, the cell process is governed by highly nonlinear equations, and hence the moderated steps are required for the sake of simplification. Next, the governing equations are presented here. So, in order to simulate this complicated electrolysis model, including multi-phase flow, I'm going to elaborate the governing equations in more details. The continuity equation and the momentum equations are solved to find the mixture density and the mixture velocities in x and y directions. In the simplified model, two species in each liquid and gas phases are allotted in the system. Therefore, two species transport equations are computed in total to obtain their mass fraction values because the n-1 number of species transport equation in each phase is only required, and the other mass fraction can be obtained by subtracting the sum of the mass fractions from the unity. And next, electrochemical relevant equations are illustrated in this slide. Since chemical reaction rate is dependent on the electrode current density by Faraday's law, um, anode current density should be calculated via Butler-Verma equations. You can see on the right side of this slide, and this requires several empirical parameters, such as reference exchange current density, which is described as J naught, and reference equilibrium potential, which is described as E subscript EQ. They can be acquired through an experimental research of circular voltammetry measurements of solution using least squares fitting method. And moreover, here, several privileged equations are used in this model. Stokes-Einstein equation and Ohm's law. Ions diffusivity can be calculated by using this Stokes-Einstein equation, whereas Ohm's law is being computed to acquire electric potential distribution. It's being calculated until it reaches a particular time, which is 0.19 seconds, and then it does not converge anymore. Does not seem like a problem that might be resolved by simply moderating the time step size, even though it is a continuity convergence problem. And why I see like that is because it still hardly converges when the consumption and nucleation source terms are allotted in this whole fluid cell zone. Therefore, it is reasonable to presume that multi-phase flow model of mine has a stiff convergence condition. Henceforth, I'm going to try not to use modules that are initially given in the fluent, but to code own governing equations, especially species transport equations, so that I can add migration flux term as an user-defined scalar in this model. Aluminum reduction style has tremendously complicated chemical processes as well as electrochemical reductions, which are coupled species transport equations. Hence, convergence problems frequently occur. Therefore, my future research will concentrate on modeling those coupled species transport equations without using provided modules step by step. Consequently, I hope I can combine migration with those species transport equations, especially for oxygen ion, which are dragged due to the electric potential distribution. Thanks for your listening.